Hi, everybody. I'm Stephen Gilbert, Associate Director of the Virtual Reality Application Center at Iowa State. And this year we're running XR Advance for Extended Reality Advance, the seminar series. A variety of speakers from around the country talking about aspects of virtual reality and augmented reality. Today we have Bas Rokers from University of Wisconsin from the Psychology Department. He'll be talking to us about cyber sickness. Bas.
Thank you, Stephen. Thanks for having me. I have to admit, this is the first time I'm doing a WebEx-based presentation. Typically, I ask people to ask me questions throughout. I'm willing to try that here, but I don't know how well it's going to go. So let's just stop me if anything's unclear, and we'll see if that works in terms of it being interactive. So what I wanted to talk about today is some work from our lab that's trying to understand the cause of cyber sickness. And virtual reality has really been an integral part of the kind of research that we do in the lab. So virtual mixed reality in our hands allows us to study visual perception in naturalistic environments. And as probably everybody in the room knows, virtual reality and mixed reality may introduce their own problems, such as cyber sickness. And so what I'll talk about today is we're going to try and work out if the study of visual perception in naturalistic environments can tell us anything about the potential causes of cyber sickness. And I'm going to do that in two parts, as you'll see. So in the first part, I'm going to basically illustrate how you can use virtual reality to ask questions that traditionally people would ask using computer displays or more common kind of experiments in the lab. And then the second part is saying, given that we now understand how to incorporate virtual reality in these kinds of designs, can we then ask this question about cyber sickness? Just to step back for a second, probably it's helpful to talk a little bit about the kind of research that we do in our laboratory. So we study visual perception in many of its guises. We aim to uncover its neural basis and the cause of perceptual disorders. And so what we will typically do is use behavioral experiments, neuroimaging, and clinical populations to ask questions about how the information that enters the eye is processed by the brain so that we can interpret our visual environment. And we do that as much as possible in naturalistic environments, and I think from this talk it will become clear why it is that we go that route. And so we do that as much as possible. And I should say that most of the work is really driven by Jackie Fulvio, who's a postdoc in the lab. He's been in the lab actually for a considerable amount of time, and is really running her own lab within the lab. And she's really pushing a lot of the virtual reality, augmented reality, mixed reality work that we're doing. All right, so if you come from a psychology or a neuroscience background, then this is your typical visual experiment in the laboratory. So we would invite an observer into the lab, we put them in front of a computer display, and then a lot of the work that we do is about motion perception. We present a motion stimulus on the screen, and then basically ask the observer to judge a motion direction or appearance of a stimulus, to basically make some perceptual judgment. And so what's pretty obvious here is that the computer display is a two-dimensional surface, and typically, even though it's not illustrated here, we also head fix the observer, so the observer is not able to move their head, so that we can carefully, so that we know exactly what the viewing distance of the observer is, and we know exactly what the visual input is that that observer sees. Of course, that's not really how perception works in the real world. In the real world, objects can move not just in image planes, they can move in all three dimensions. And another thing is that observers typically are not stationary. They are moving as objects around them move. And so the problem that an observer has to solve is a much more complicated problem than the one that we typically encounter in the laboratory. And so a lot of things that, as you will see, become available when you use virtual reality are trying to bridge that gap between traditional experiments in the laboratory and what we need to understand about perception to account for performance in the real world. And so virtual reality allows us to a large extent to bridge that gap. We are not quite in a completely naturalistic environment, but we are able to simulate a naturalistic environment while at the same time keeping very tight control over the kind of visual information that's being presented. And that's how we can ask or quantify perceptual accuracy, for example. And so there'll be an image, you'll see this image recurring, as I'll show you what actually is being presented to observers in the kind of experiments that we do. But this is a typical illustration. This is an observer looking at a visual scene. What you see on the display here is actually going to be presented to the two separate eyes. So the left half of the image goes to the left eye, the right half of the image goes to the right eye. Of course, the brain perceptually integrates those, and you have a single unitary percept as a result of that. Right, so the first thing that we wanted to do and that we need to do, what we want to quantify perception in 3 dimensions, is we need to come up with tasks that allow us to put a number on an observer's perceptual performance. And initially, and still, I think a lot of things are unknown about how perception or the study of perception in 3 dimensions can be translated from more traditional approaches, looking at perception in 2 dimensions. And so what we did is we developed a paradigm that we call 3D Pong. So this is basically, well, it's a direct lift of the classic Atari video game Pong, where you have a ball that moves in the image plane. You have a paddle as the player that moves at the bottom of the screen, and you adjust this paddle to intercept the ball and make sure that it doesn't run out of the playing field. So I'm going to show you how that works in 3 dimensions through a couple of slides so that you have a good idea of what the task is. And then I'm going to show you some surprising results that come out of an experiment like this. So here what I'm showing you is a top-down view where the observer is represented by 2 eyes looking at a target that can move in any direction around the clock in 360 degrees. And so the important thing to take away here is that this target can move away or towards from the observer, and it can move leftward and rightward. We constrain the target to not actually move up and down because it makes things more complicated and it's not necessary for the kind of things that we want to illustrate here, though of course in the real world objects have been known to move up and down as well. So this target will move, it will then disappear, but to the observer now you have a percept of the motion direction. And once the target disappears, we present the observer with a paddle, and the observer can adjust this paddle along this circular orbit. And we ask the observer to adjust the paddle so that it would have intercepted the target had the target continued along its trajectory. And that gives us a response, and that response is a direct estimate, or is the observer's estimate of the motion direction that's being presented to the observer. And then finally, what we can do is we can quantify that performance, for example, by calculating the percentage of time that the observer intercepts the target, or we can calculate the difference in the angle between the setting made by the observer and the actual motion trajectory. And there's a number of other ways we can quantify it, but it gives us now numbers that we can directly compare. I think you guys turned off the mic, but if there's any questions at this point, let me know. I'll wait for like 15 seconds. If I don't hear anything, I'll continue. All right, I'll continue from here. All right, so good. Is that perceivable at all? Like if it's high enough contrast, is that what you're thinking about? Yeah. So we don't explicitly detect that. So there will be some fraction of the trials in which the observer basically is guessing because they didn't see the stimulus. We'll see performance in a second. I think those situations are very rare. When People make errors when they miss the interception. They do it in a systematic way, which tells us that they still see the target, but they misperceive its trajectory. Does that make sense? And then the other thing I should say to that is that these stimuli are all presented at high contrast. So it's not a detection kind of experiment. It's not that the target itself is hard to see. You might, of course, miss it because it's only on the screen for 1 second, but it's not because it's low contrast. Other questions? Oh, here we go. How is the paddle controlled by the participant? Yeah, so that's a good question. So the paddle is constrained to run on this circular orbit. That means that really it can only move clockwise and counterclockwise, and we just ask the observer to push the arrows on a keyboard, either leftward or rightward, until they're happy with their adjustment, and then they push the spacebar. So there really is not a lot of like high technology there. It's just we constrain the paddle positions so that it becomes a very simple task, for, at least from the perspective of the observer. Great, this is a good way to like keep up with chats. I'll make sure that I'm not missing anything here. Good. Other questions? I'll just monitor this chat window, and if things come up, that'd be a good way to do it. And also, yeah, auditory interruptions worked as well, so feel free to do that as well. Okay, so this is the basic setup. I'm now going to show you what it is that the observer actually sees, because I think it helps understand what the space is in which the observer is performing the task. Now, let's move. Okay, so here we get a view of one of the eyes. So this is the observer wearing the VR headset, in this case an Oculus Rift DK2. We're now moved on to the CV1. It would work very much the same. This is the single view from a single eye. And there's a lot of stuff here that's not going to be central to the, or that are peripheral to the experiment, but that are necessarily there because they help observers' performance. The first thing is that we always present a 1/f noise background. So that means that this peppery background is here because we match it with a background in the other eye. And that background is presented at the focal distance of the display, which for the DK2 is 120 centimeters. And so that allows observers to self-monitor vergence and version, basically eye position. So it's not, you're not swimming around, and the observer can make sure that they actually have correct fusion. This aperture to the observer will look like a 15-degree aperture, so that's relatively large, and that's where all the action happens. This 1/f noise background is just there, but it's not going to be relevant other than for eye position in the experiment. We then present a number of fixation crosshairs, which is also there to indicate where the target is going to appear. It's going to always appear in the center of the display. And also to monitor correct versions between the two eyes. We have a target here. As you can see, this is a high contrast target. It's presented right at fixation, as long as the observer is fixating where we ask them to fixate. And so it's not going to be, well, it's not going to be easy to miss, right? This is a very obvious target. Here it's stationary. Actually, when the observer sees it, it's already moving, and it's going to be moving for 1 second. As it would here, and then it disappears, and you see this paddle appear. And so then the observer is the one who's controlling the motion of the paddle, and the observer would adjust it so that they believe it would intercept the trajectory of the target. So a couple of things to point out here. Everything here is projectively correct. So that means that there's perspective cues in here. When the paddle is coming towards the observer, it's running in this circular plane. It's actually moving closer to the observer, and as a result, it's becoming larger. And the same is true for the target. So it's going to be hard to see because these changes are very tiny. But this target, as it's coming closer to the observer, it becomes larger. So this display, when you consider the one eye only, contains monocular cues to 3D motion. It contains all the cues, all the 3D motion cues that you would want to have in your display. And we know that observers exploit monocular cues to 3D motions. It's not the only thing that they exploit, but it's one of the pieces of information that they use in order to perform a task like this. Now, we have a VR setup, so this is not the only view that they get. They actually get two different views, one for each eye. And so we get a left eye view, that's the same one that I just showed you, and we get a right eye view. If you're able to fuse these two images, if you're able to free fuse, you'll see that in fact you now get a 3D percept, because even though they look very similar on their face, there are slight differences between the image of the target and the paddle in the two displays that are consistent with this object with these objects being 3D objects moving to 3D space. Does that make sense? All right, and so what you're shown here are the binocular cues, right? So here you have both monocular cues that are in each individual image, and you have binocular cues, which are the differences in the images in the left and right eye. And we know that the binocular cues also contribute to 3D motion perception. So here you have two sources of information that both tell you about the trajectory of this target over here. Okay. So now we have all the pieces of the puzzle to start quantifying performance in a 3D world. And this could be a very boring slide, if not for the fact that people make surprising and systematic errors. So let's walk through what this plot actually shows. Here, what I'm simply going to plot is the reported direction by the observer as a function of the presented direction. So this is the target presented direction. This goes from 0 to 360 degrees, which goes from purely rightward to away from the observer, and purely leftward towards the observer, and then again purely rightward. So one thing to keep in mind is that 360 and 0 are exactly the same direction of motion. They're both rightward because this is on a circular scale. So if a point lies here, it's actually very close to a point lying over here. The same is true for the reported direction. That's on a circular scale as well. And if observers were vertical, that is, they would always report the correct direction of motion, then all of their points should lie on this diagonal line. When I present an object that's moving away from the observer, they should report that object is moving away from them. Right? And so all these points would lie on the diagonal line. And it turns out that that's not what happens. So what you actually see in your performance is that, yes, there are a lot of points that lie on this positive diagonal, but of course some variation around it because observers are not perfect. But you will also see a lot of points that are clustered around the negative diagonal. And this is not just for one participant. This is each individual data point is one trial for one participant, and this is across 38 participants, and we've replicated this a number of times. It's a consistent result, and it turns out that it's an inherent limitation of the relatively small interocular separation between the two eyes. So what does this mean? Let's make that more explicit. So when we have an observer that's seeing an object that's moving towards them, or is presented in an object that's moving towards them, in a good fraction of the time when that happens, the observer in fact reports the object moving towards them. But there's also some fraction of the time when the object moves towards the observer when they actually report it as moving exactly away from them. So they inherently confuse the direction of motion in depth. And that's in fact what all of these points in the negative diagonal have in common. They give you a correct estimate of the lateral component of the motion, but they misreport the motion in depth component. So they'll report approaching as receding and receding as approaching. And as I said, this is a fundamental feature of 3D perception, not just in VR, but under relatively low contrast conditions in the real world as well. And I'm happy to talk about that more at the end of the talk. There's other features in this data that I won't go into unless somebody wants to hear more about it. One thing that you can see is that you have a larger proportion of dots that are lying in the bottom part of the figure than the top part of the figure. What that means is that there's a bias for observers reporting objects as moving away from them rather than towards them. Right. This is a rich data set that we are currently exploring. There's lots of things in here which are all obtained by virtue of now having awesome VR technology. and an ability to quantify perception in a virtual reality task. Okay, so this should be of somewhat of a concern to you for a number of reasons. First of all, it'd be ecologically not so great if observers habitually misreport the motion of direction and depth of objects. It would mean that, you know, an object that's coming right at you, you would judge as moving away from you, and that would not be good. The other thing is, of course, that in the real world, we don't really see this happening. And so there must be other things that are present in the real world that are not present in the experiment that I've shown you so far. And one of the things that is head movement contingent updating of the display. So I did a little bit of a cloak and daggers because I didn't make this explicit in the beginning, but what I showed you so far are displays that only contain monocular and binocular cues, but they did not contain any head movement contingent updating of the display. So when the observer moved their head, the display remained the same. Now in VR, of course, now we have head tracking, and so we can incorporate head tracking into this experiment and see what happens. And so as many of you well know, head movement will produce motion parallax, and this is an additional cue in addition to the monocular and binocular cues to depth. The objects over here are clearly perceptually farther away to you than the objects in the bottom of the image over here. And what we can now do in this kind of design where we ask the observer to play 3D Pong is we can ask what's the contribution of head movement to perceptual accuracy. And I should be a little bit more specific here. It is clear that large head motion produces these kind of signals. And what we do in the context of this experiment is we actually ask the observer to keep their head still. And in fact, it's to their benefit to keep their head still because all of the action is right at fixation. And they should look at an object right at fixation in order to perform the task. Because we have head tracking, we can quantify how much they're actually moving their head in the 1 second that the stimulus is on the screen, which is the 1 second in which you can actually extract information based on head jitter or head movement. And what you see is that the amount of movement in that 1 second is relatively small. It's on the order of a couple of millimeters. And if you look at the rotation, it's this is in arc minutes over here, so it's, you know, it's a fraction of a degree of rotation over the 1 second that the stimulus is being presented. So these are tiny, tiny movements, which we call head jitter, because they're small and they don't appear to be under voluntary control. The observer is reporting that they're stationary, but in fact their head's moving, and we can now update the display according to those movements. And so now we can ask what happens if we enable head tracking. And you can probably already see it at the top over here. It turns out head jitter enhances 3D perception. And it enhances it in a particular way. It enhances it most in these directions toward and away from the observer, where they were making most of the mistakes based on monocular and binocular cues only. So it looks like head jitter helps you disambiguate the ambiguity that you have in the towards and away component of 3D motion trajectories. And this is not something that you would ever get from a corresponding 2D motion experiment, because head jitter doesn't really play a role if you're judging the direction of motion on a computer display. It only becomes relevant if you're trying to judge the direction of motion towards and away from you. All right, so now we can ask a more fine-grained question, or well, actually we should be careful in quantifying this difference. Because when we turn off head jitter, the current VR displays have a relatively coarse spatial resolution. And so one of the reasons why you might see this improvement may be because head movement effectively increases the spatial resolution of the display, because at slightly different times you get a slightly different subsampling of the grid of the display. And so we wanted to make sure that that was not the cause of this effect. And so what we did is we introduced a third condition where we lag head motion updating. So when an observer moves their head, the updating of the display is somewhat delayed, and it can be between 0 and 500 milliseconds in this case. 500 milliseconds is really a lot. We'll see on subsequent slides that it doesn't need to be that large. If you introduce lag in your updating of your display, then you effectively abolish the benefit that you were seeing before. So you get poorer again. And in fact, we see that observers, in response to a lagged or fixed condition, so they either head movement is not changing the visual display, or head movement is changing the visual display in a lagged manner, we see that observers are actually reducing their head motion, which we think they're doing in response to motion sickness because they now have a cue conflict, which is something that I'll go into much more in the second part of this talk. We can then ask, how small does the lag need to be between head motion and the updating of the visual display in order for the observer not to be thrown off by it, for the observer not to take a hit in performance? And it turns out that the observers are highly sensitive to lag. So here we have three conditions in which the updating of the display is either 1 frame, which is as good as we can get, so head motion gives you immediately on the next frame gives you an updated view, 2 frames or 3 frames, or you can do it in some random way. And we see that as we are reducing the lag, performance in terms of the percentage of interception still improves. So even a lag as small as 14 milliseconds can still improve performance compared to 27 milliseconds. And if you look at the amount of head motion that the observers actually exhibit, we also see that they start suppressing, or they suppress more and more as the lag increases, the amount of head motion. So we've not yet reached the saturation point. One of the nice things about the new hardware coming out is that the frame rates are going up, and so we can now go to sub 10 millisecond lags, and we're currently investigating what the effect of that is on perceptual accuracy. Okay. Good. I'm just checking for time. All right, so interim summary so far. Head jitter enhances perception in a 3D world. Display lag impairs perceptual performance. And now, of course, the natural question is, can we use these insights to identify the cause of cyber sickness, which is what we all came here for in this talk. Right. We are very much swayed by, I think this is probably the mainstream explanation of motion sickness, which is that motion sickness is due to sensory cue conflicts. Sensory cue conflicts produce motion sickness, and it's specifically conflicts between the visual information that the observer receives and the vestibular information that they receive as well. And both of these sources of information tell the observer about motion through the environment, either through visual information or what their vestibular organ tells them. That leads, and this is what we concluded, this leads to the prediction that if an observer has greater sensory sensitivity, they should exhibit a greater propensity for motion sickness. And as far as we are aware, this has never been tested. And there's a question that rises on top of that, and that is sensitivity to which visual cue. It's pretty clear that the vestibular system plays an important role, and we know that people that lack a vestibular system do not suffer motion sickness, and people that have a disturbed vestibular system actually are much more prone to motion sickness. But we don't know anything about the visual cues, or of which of the visual cues that I've introduced are the ones that are underlying cyber sickness. And so now we're in an excellent situation to ask that question. And so what we did is we designed a slightly simpler version of the experiment that I've shown you so far. Here we have a visual display that contains a number of dots that are all moving in the same direction, either towards or away from the observer. That produces, by viewing it through a VR display, a percept of a field of dots either moving towards or away from the observer. And the observer simply reports to us if the motion was towards or away from them. So there's no 360 degrees here. This is purely towards and away. It's a two alternate force choice task. This is a screen grab of what it actually looks like in the VR headset, as good as we can show it on a 2D screen, of course. So what should be obvious here is that you have monocular cues. What will be less obvious, but you'll have to take my word for it, there's also binocular cues in here, so these dots are moving slightly differently in the two views. What is not here so far is motion parallax cues. This is as if the observer is completely stationary. We embed this field of dots in a 3D room just to get the observer comfortable with the fact that this is a task that's performed in a 3D environment. Otherwise, it's irrelevant to the task, but it just gives them a sense of immersion. And we can now split out, or to the best of our ability, split out different cues to 3D motion. And so what we wanted to ask is which of these cues is predictive of motion sickness, or sensitivity to which of these cues is predictive to 3D motion susceptibility. So we can present stimuli that only contain binocular cues by just presenting dots that are moving in horizontally opposite direction in the two eyes. Or we can present stimuli that only contain monocular cues by effectively not showing anything in one of the two eyes. We can combine those two cues into a stimulus that has both binocular and monocular cues, which we call the combined cue condition. And then we can present what we call a full VR condition, which is the monocular and binocular cues combined, plus the motion parallax cues. And there's unfortunately no way to show motion parallax cues by themselves. They always need to be dots present. So the way that we can distinguish the contribution of motion parallax is by directly comparing the full VR and the combined cue condition, because the difference between those two is that the full VR stimulus does contain motion parallax cues, whereas the combined cue condition does not. We assess sensitivity by varying motion coherence in the display. So here's a stimulus that is 100% motion coherent. That means all dots are moving in the same direction. Here's a stimulus that is 50% motion coherent. That means that 50% of the dots are moving all towards the observer, and the other 50% are randomly refreshed on every stimulus frame. That's going to make the task harder, and so you would expect the observer to have a smaller percentage of the time in which they report the stimulus is moving towards. We can also present stimuli that have dots that move away from the observer, and then of course the observer should rarely, if ever, report that the stimulus moves towards them. And then gives us a psychrometric curve. It gives us a measure of sensitivity, and now we can quantify sensitivity by looking at the slope of this curve. So if an observer is highly sensitive, that curve should look something like this. It should be a steep slope. We call that greater sensitivity. If the observer is less sensitive to a particular cue, then they would have a less steep curve, and we would call that poor sensitivity. Okay, so now that we've set that up, we can quantify visual sensitivity to motion cues across observers. And we did this in almost 100 observers. We showed each of these different cue conditions, and we quantified that sensitivity in this amount of slope, where larger numbers here mean greater sensitivity. Now, the first thing to see is that within a particular cue, let's take the monocular cue for an example, there's quite large variability in observers' variability to that cue. So some observers are highly sensitive to that cue, whereas other observers are pretty much not sensitive to it at all. There's an interesting wrinkle here that if you look at binocular cues by themselves, it looks like a very large proportion of observers are not sensitive at all to binocular cues in these kind of stimuli. We think we know why that is, and ask me during the Q&A if you want to know more about that. These triangles over here indicate mean sensitivity so that you can compare sensitivity across these four conditions. One thing that you should be able to take away from this is that if you have both the binocular and monocular cues combined, mean sensitivity is greater than when you have either one of these cues in isolation. And if you add motion parallax, you do not significantly get greater still. But here still there's large variability when all cues are presented in the sensitivity to these cues. Right? And so remember, what we're going to do later is we're going to get an estimate of the sensitivity to motion sickness. And then we want to know if the individual sensitivity to a particular cue is related to their propensity for motion sickness. So now that we have the first part of it, we have assessed sensory sensitivity, we can now assess the second part, the propensity for motion sickness, which is a little bit more of a nefarious experiment. So what we did is we had observers view 22.5 minutes of binocular head-fixed video, which was chosen to introduce at least moderate senses of motion sickness. So these are videos of relatively small, well, this is a drone flying. We also have an RC car driving around, where clearly the observer is not in charge of the motions that are being presented to them. And so, as we'll see in a second, this introduces moderate amounts of motion sickness in some, but not all of the participants in our experiment. We then assess an observer's motion sickness symptoms by using the SSQ, which is being originally developed to assess space sickness. And we find it to be a reliable indicator of actual motion sickness symptoms. People that are, that don't feel so great and are relatively easy to distinguish from people that actually don't have any symptoms at all. And the scores that they produce, even though this is self-reported, are usually in agreement with that. So one of the questions is asking, please rate your nausea, and you can do that on a 4-point scale. And then all gets added together. Just to give you a sense of that scale, it goes up to 100 and some points. This is our baseline SSQ measure. So this is when the observers just get into the lab. They haven't done anything yet. We get their motion sickness score, and that's modally at 0, and there's a small distribution. But basically, nobody really is very motion sick before they start the experiment. We then ask them again after we do their sensory sensitivity assessment. So this is judging if dots are moving towards and away from them. There's not a lot of motion content in there. It's not designed to make these individuals motion sick, but their symptoms are slightly increasing. Right now, some people are in the moderate range, but most of them have very few, if any, symptoms. Then we look at their motion sickness after they complete the video viewing that's designed to introduce motion sickness. And then the situation gets quite different, where a good number of people now are not feeling so happy. So we're able to induce in some observers, and we don't want to get too far out, but we want to induce it in some observers. And importantly, we want to have a distribution of motion sickness. So some people still don't seem to suffer even after watching these extended videos. Okay, so now we have all the pieces of the puzzle, and we can start relating these two measures to each other. We can ask, does greater sensitivity to a particular visual cue introduce a greater propensity for motion sickness? So we can do that by linking cue sensitivity and motion sickness. We plot greater sensory sensitivity on the horizontal axis, greater sickness scores on the vertical axis, and we can do that across all of these cues. For binocular cues, there's really no relationship between an individual sensitivity to binocular cues, to 3D motion, and motion sickness. For monocular cues, there's a hint of a relationship that doesn't survive repeated comparisons. For combined cues, there's no relationship. But what we see is in a full VR cue, we get a quite strong relationship between an individual sensitivity, or maybe an easier way to think about it is an individual's performance on a motion discrimination task in a full VR condition, and their propensity for motion sickness. Now, people that are highly motion sick also are performing very well in this kind of situation. So this gives us a predictor for motion sickness, and especially gives us a predictor which says that motion parallax, or sensitivity to motion parallax, is what predicts your susceptibility to motion sickness. So your sensitivity to full VR predicts motion sickness. So to summarize the data up to here, motion parallax in the first part of the talk was shown to enhance perceptual performance, but in the second part of the talk we showed that sensitivity to motion parallax actually causes motion sickness. And so that leads to, to us, that illustrates the irony of VR, because those who benefit the most, those who perform the best, are also able to tolerate it least because they get the most motion sick. And so we're now in a situation to start tackling some of the follow-up challenges. It's, I think, clear to everybody in the room that cyber sickness is a major barrier to virtual reality adoption. Now that we have identified its cause, we can work on reduction and prevention. I'm happy to talk about that more in questions. But you can reduce these cues either by improving the engineering to reduce the lag between head motion and updating of the display, or to get better head tracking. Or you can prevent it by somehow making these motion parallax cues less reliable, so that observers can basically discount them. And that's something that we can talk about more if interested. And then the next thing that we're particularly interested in is we want to determine the role of cyber sickness in mixed reality. So far, what I've shown you is that in virtual reality, we understand why people get motion sick. And we think in mixed reality, the issue is similar, but not exactly the same. And what we likely think is going to happen, and we have some preliminary evidence there, is that your propensity for motion sickness under these conditions is going to be an interaction between device calibration, where the interpupillary distance, according to the device, is going to play a large role. Virtual real content registration, obviously, the amount of swimming that virtual objects do in front of the real background, and the amount, type, and location of virtual content. So if you have relatively sparse virtual content, then probably it's not going to be as much of an issue. But if you start filling in more of your visual field with virtual content, then I think it's very likely that these motion sickness issues are going to crop up. And with that, I wanted to thank all of collaborators that made this possible, specifically Jackie, who's working and is still working tirelessly at this research, people in the lab, and of course our collaborators in industry, and the people who made this research possible. Thank you very much, and I'm happy to take any questions.
We're going to pass the mic, or overhead. Okay. Any questions? If you're out remotely, you can post them to the group, or in the room here. So, Bas, what are some of your ideas for prevention?
Yeah. So prevention. Well, so there's some obvious things you can do, right? So one of the things is one of the things we see is that observers stop moving their head. This is some of the data that I alluded to halfway through. So if you look at something like this, let's see if I can get the build. So if I go here, no, I don't know how that works. So I didn't have time to go into more detail, but one of the things that you're seeing is as observers start getting motion sick, they also stop head jittering. So they actually suppress their head motion. So you now have a real-time index into how good or how bad the observer is doing. And one of the things, of course, you can do is you can just reduce the amount of motion that you present in your virtual environment in order to head that off, right? If people stop moving, that means they're not doing great. So that's one thing. Another thing that I'm particularly interested in is making cues unreliable so that people start discounting them. So if you, over time, can convince somebody that in this particular environment, motion parallax is not informative, it turns out that people stop using that cue, and the prediction is that then also they're not going to get sick because they're not really processing that cue actively.
We have a question from a student named Alex who is noting that a lot of video games in VR now use teleportation as a way to reduce optic flow. So I just hop places. And
Yeah.
but is there a way to maybe this is along the lines of learning to ignore it, but he's talking about can you do training to sort of reduce the effect of the optic flow, or because someone...
Yeah, so reducing the effects of optic flow is along the lines of what I suggested in the second part of my previous answer. It's basically teaching observers that in this context, optic flow is not a reliable cue. Teleporting is a good fix, but it's a kludge, right? It's ultimately we want to get to situations where we can provide VR content in the same way we would like somebody would see real world content, and taking out optic flow by teleporting people around, I feel is like missing something and doing a disservice, even though it fixes the problem at hand.
So how about, do you think, a lot of people complain about the SSQ being self-reported. Do you think this head jitter is a good enough indicator that we could rely on it instead as a physiological measure?
That's a good, well, yeah, we didn't, so now that you mention it, we should of course have just correlated SSQ score and head jitter. And we haven't done that, so I'll add that to the list. Yeah, my anecdotal experience is that SSQ is a good predictor of motion sickness because you can just see, like, people that get a high score, you can tell that they're getting a high score because they're showing the classic symptoms. They get a little sweaty, they get a little more quiet. Some of them get a little burpy.
Yeah.
So yeah, the fact that it's self-report hasn't been an issue in our hands, at least.
I think though, even though what you're saying is true about the SSQ, it's hard to compare across individuals because the sensitivity is so different.
Yeah, so that's probably something that wasn't obvious here. When I showed you these scores here, when we look at sensitivity, this is actually a change in motion sickness. So we norm, every person takes a pretest. And so it's the change that they report, right? So they take the SSQ before they do anything. And we look at change in their score before and after. So at least that helps to norm it a little bit against their own performance.
Well, all right. I'll send out a survey on the chat online. I put a survey link, and you can respond if you like this, if you have suggestions for improving our seminars. There's going to be another one next week with Walter Boot, who's going to talk about older adults in VR and how they fare. And so thanks a lot. Thank you, Bas.
Okay, thank you.